All right, in this video, I'm going to talk about integration by parts, and I know that you may have seen this already in Calc 1, but never hurts to review. So for integration by parts, you can break an integral into two different pieces, a u and a dv. So those are pieces you would have to choose. And the formula for it is then you would multiply u times v minus the integral of v du. And I want to do just a quick little proof, kind of a little informal proof here. What I'm going to do is I'm going to start with the product rule. So the product rule would say that if I took the derivative of u times v, both being functions, I would then take the derivative of u and multiply it by v, and then add to it just leaving u alone and multiplying by the derivative of v. So the product rule for derivatives gives us that. Now, if I integrate both sides of this, so I'm going to take the integral of this side, I'm going to take the integral of all of that. The integral of a derivative undoes that derivative. So on the left-hand side, I would be left with just u times v. On the right-hand side, if I split this up, I have an integral of u prime v plus an integral of u v prime. And if I solve for the integral of u v prime, so I'm going to solve for the integral of u v prime. This would leave me with uv minus this guy right there, so minus the integral of u prime v. And if I do a little substitution here of saying that the derivative of v is dv, and the derivative, sorry, that is a minus sign right there, and the derivative of u is du, I get the formula that we had up above. So the trick on parts is to pick a u and pick a dv. So you want to split your integral that you're looking at into two different pieces that are multiplied together. Then what you need to do is find du by taking a derivative of u, and find v by taking the integral of dv, and then plug into the formula. So then plug into the formula. All right, let's do an example. So let's integrate 2x times the cosine of 5x. Okay, so on this one of the tricks of choosing your u and your dv is that for your u, you want to pick something that when you take the derivative of it, I think of it as like decreasing that value. It makes the derivative have a degree less than it had before. It's sort of one of the little hints, I guess, on this. So what I want to do is I want to pick u as 2x, and I'm going to pick dv as the cosine of 5x, and I'm going to include the dx with that dv. Now I need to find du and I need to find v. Just notice my organization on here. You may do this differently, and that's totally fine as long as you're finding the same quantities. All right, so now du is the derivative of u, so that's 2 dx. And the integral of cosine is sine. 5x stays in there. And then because of u substitution, we would have to divide by the derivative of the inside part. So I sort of start to make a little shortcut here where if the derivative of the inside part is a number, I divide by it. If it's not a number, I can't do this. I can't just divide by it unless it is specifically just a number. So I took the derivative of the inside part, which is 5, and I divided by it in that integral. Okay, so now this integral is equal to u times v, so 2x times 1/5 sine of 5x minus the integral of v du. So minus the integral of v 1/5 sine of 5x, all that multiplied by 2 dx. So for the first term, I've got 2/5 x, and that's multiplied by sine of 5x. And for this next integral, I'm going to look at the sine part first, the sine function. So the integral of sine is negative cosine. So that's going to make that a plus. The integral of sine was negative cosine. I still have that 5x. Now I just integrated again, so I've got to divide by the derivative of the inside part. I've got to divide by 5. That's going to give me a 25, and I still have that 2 in the numerator. All right, done. Just add C. Okay, so there's our first example of integration by parts. Here's a second example. I want to find the integral of x squared times, well, let's do that cosine of 5x again. Okay, now what I want to show you on this one is a little bit of a different way to do integration by parts. This is one that it would require you to do integration by parts twice. You would choose u as your x squared. You would choose dv as cosine of 5x. You would plug into the formula, and your minus the integral of v du would end up having an x in it. And then you'd essentially have to do the integral that we just did. So you'd have to do integration by parts twice. So here's a little trick. This is called tabular. Tabular is integration by parts. It is parts. So it does the multiple integration by parts for you, but the only trick is that derivatives have to go to 0. So you can use this if what you choose for u goes to 0. All right, so same as before, we have a u and we have to pick a dv. Same exact thing. And we're going to pick the same things that we would have picked. So if we did this regular parts, we would choose u as x squared. And we would choose dv as cosine of 5x. Now, same as before, for u, we would find du, so we would take a derivative. Now, we're going to take a derivative all the way down until we hit 0. So the derivative of x squared is 2x. I'm going to take another derivative. The derivative of 2x is 2. I'm going to take another derivative. The derivative of 2 is 0. So you can see how I took a derivative until I hit 0, and that's when you know that you can use this different way. So now, for this other side, same as before we integrated, we're going to do the exact same thing. We're going to integrate cosine of 5x, but we're going to keep integrating until we hit the same row that 0 is in. All right, so I'm going to integrate cosine. The integral of cosine is positive sine, and that would get that 1/5 out in front. Same thing, I'm going to divide by the derivative of the inside part. Integrate again. The integral of sine is negative cosine. And I've got to multiply by the derivative of the inside part. I'm going to get a 1 over 25. Going to integrate one more time so that I have the exact same number of rows that I had for the derivative. So I've got to integrate one more time. Derivative of cosine is positive sine, but it keeps that negative out in front of it. And we've got to divide by another 5. So this would be 1 over 125, the derivative of that inside part. Now I'm going to multiply down this chart that I made diagonally. So I am going to multiply those quantities. And because of the minus v du in the formula, the signs end up oscillating on these. So the first multiplication is going to be positive. The second one's going to be negative. The third one's going to be positive. And if this kept on going, it would go positive, negative, positive, negative. It always starts with a positive. And again, always goes positive, negative, etc. Okay, so this first diagonal here has x squared multiplying 1/5 sine of 5x. The next one has the next diagonal has a negative 2x times a negative 1/25 cosine. So negative times negative is positive. I've got a 2 over 25 and then x times cosine of 5x. The next diagonal is multiplying 2 by negative 1/25 sine of 5x. So that's going to give us a negative sign there. 2 over 125 sine of 5x, and we add c and we're done. If you don't like tabular, don't use it. You don't have to. You can always do this by just using integration by parts and doing it multiple times. You have to know both of them. So unfortunately, tabular is nice and easy, but there aren't always integrals that will have that derivative equal 0 at the bottom. I'm going to do an example of one of those next. And so you can't always use tabular, but you can always use parts. I like both because this is such a simple calculation, and I tend to make mistakes when I have to multiply through the negatives and all of the constants along the way. All right, so let's do an example. Let's do an example where we can't use tabular. So let's do the integral of the square root of t times the natural log of t dt. Okay, and let's integrate this from 1 to 4. Okay, so my first intuition looking at this integral is actually to do a u substitution, but in order to do that, I would have to choose u as an inside part, and then that doesn't make any sense. I've got this square root of t out in front that doesn't help it. So to do parts, we need to choose a u, we need to choose a dv. Now, if I choose u as root t, because that I think is intuitively what a lot of people would do, my dv would be natural log, and then I would have to integrate that. And we don't know how to do that without another, actually you can integrate it, but it's an integration by parts. So it would be parts within parts. But we do know how to take the derivative of natural log of t. So we want to specifically choose u as our natural log of t, and then dv would end up being the square root. So the square root is the same thing as something raised to the 1/2. So we take a derivative of natural log of t, that's 1 over t. And I'm going to integrate t to the 1/2, so I have to add 1 to that exponent. That's 3/2. Divide by 3/2, which is the same as multiplying by 2/3. Okay, so for this integral, I've got 2/3 t to the 3/2 times natural log of t minus the integral of v du, so that's minus 2/3 t to the 3/2 times 1 over t, oh, I forgot my little dt right there, dt. Okay, so on this one, now I can, the first integral is going to stay the same. Natural log of t minus, I've got to combine these t's before I can integrate. So t to the 3/2 divided by t, that's going to decrease that by 1, that exponent. Okay, now I can integrate that. So I've got 2/3 t to the 3/2 natural log of t minus, I'll add 1 to that exponent. So adding 1 to 1/2, I get 3/2. And then I've got to multiply by another 2/3. That would give me 4/9 out in front. Now, I haven't forgotten about these bounds, but now is when we need to plug those bounds in. Okay, so plugging in 4, I've got 2/3 times 4 to the 3/2 times natural log of 4 minus 4/9 times 4 to the 3/2 minus, I'm going to plug in 1, 2/3, well, 1 to the anything is 1, so that's just times of 1 times natural log of 1 minus a negative, minus because it was lower bound, another negative because it's a negative quantity on that term, 4/9, and then that's multiplied by 1. And I can simplify this because 4 to the 1/2, so 4 to the 1/2 is equal to 2. That's a square root of 4. And then I'm going to cube that. So I get 8. Okay, and 8 times 2 is 16. So 16/3 natural log of 4 minus, and then we get 4 times 8. So that's 32/9 right there. Natural log of 1 is 0, so that term goes away, plus 4/9. And combine those terms, 16/3 natural log of 4 minus 32 plus 4, that would be 28. Okay, so there's an example where we couldn't use tabular just because what we have to choose as u, if we kept taking a derivative of that, we would never hit 0. In tabular, that kind of has to happen in order to use that technique. All right, one more example. So one more example. Let's do the integral of e to the 2x times sine of x. All right, now this is an example. It's different from many other types of examples where what happens is because e repeats itself in a derivative or an integral and sine repeats itself, sine, and cosine, we end up in our formula for parts back to the same integral we're looking for. And then we're going to add that to the integral we're looking for. Okay, I know this sounds strange, but that's kind of the idea. So we're going to do 2 integration by parts and then we're going to add one side to the other, or one integral to another. Okay, so for the first integration by parts, u is equal to e to the 2x. So if I take the derivative of that, I get 2 e to the 2x dx. dv sine of x. So that means v, I'll integrate that, I'll get negative cosine, right? Negative cosine of x. Okay, so I'm going to leave this integral that we're looking for in this formula the whole time. We are looking for the integral of e to the 2x sine of x. So first integration by parts here, u times v is negative e to the 2x cosine of x minus the integral of v du. So that's minus a negative, because the negative in front of cosine, 2e to the 2x cosine of x dx. All right, so there's the first step. Now I'm going to do another integration by parts. I'm going to choose u. I'm going to choose it as the 2e to the 2x. If I put the 2 in there, it distributes it for me, and I don't have to worry about distributing it later. So then du is going to be 4e to the 2x. My dv is what's left over. That's cosine of x dx. And then v, if I integrate cosine, that's sine. Okay, so now I'm going to rewrite what I started with. We're trying to find the integral of e to the 2x sine of x. In our first formula there, we came up with negative e to the 2x cosine of x plus, now my new integration by parts. U times v gives me 2e to the 2x sine of x minus the integral of v du. So minus the integral of v du. So that's 4e to the 2x sine of x. Okay, so now here's where all the magic happens. On the left-hand side, I've got e to the 2x sine of x. On the right-hand side, I've got e to the 2x sine of x and the integral of it. Over here, I've got one of those integrals. Over here, I have 4 of them. So I am going to, on both sides of this equation, I'm going to add 4 times the integral that we're looking for. So over here, I'm going to add 4 times the integral that we're looking for. And this only happens because of the repetitive nature of e's and sines or cosines. So you can recognize this is an easily recognizable integral. You've got e's and sines, and you know you're going to have to do this integration by parts twice and then adding these integrals together. All right, so now if I do this, I'm going to have 5 of those integrals that we were looking for, e to the 2x sine of x. On the right-hand side, those end up canceling. That's the whole reason I added it to the other side. So I'm left with negative e to the 2x cosine of x plus 2e to the 2x sine of x. And this was the integral we were looking for originally, just the integral of e to the 2x over sine of x. So all I have to do is divide by 5. So the integral that we were looking for, e to the 2x sine of x dx, I just have to divide by 5. So I'm going to divide this entire right-hand side by 5. Negative e to the 2x cosine of x plus 2e to the 2x sine of x. And there were no bounds on this one, so let's add c. Okay, so once again, easily recognizable. E's, sines or cosines. Integration by parts twice. Leave everything else when you do that. You will end up with two integrals that look exactly the same. Put all of those integrals that look the same onto one side of the equation and then solve for the integral that was your original. So divide, you'll get a number here out in front. Divide by that number. All right. You can notice that these are definitely very unique integrals. They definitely have stuff that repeats in there. Okay, so I think that is it for this video.